The Webb peers such a long way out that it's catching light that has been voyaging for more than 13 billion years. However, the universe has been expanding, and thus the light has been stretching. For the most distant galaxies, we are looking back in time nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we refer to as the singularity. As of now, this is how we interpret the Big Bang hypothesis anyway. The James Webb Space Telescope, JWST, has revealed significant secrets about the birth and evolution of the universe, leaving us bewildered. Famous physicist Brian Cox has proclaimed that the striking revelations made by the JWST might actually reshape our perception of the universe as a whole. Join us as we dig into these new divine disclosures that promise to upset our understanding. The James Webb Space Telescope, named after the distinguished NASA Administrator James E. Webb, stands as a wonder in current galactic investigation. This telescope represents a huge technological leap forward from its ancestor, the Hubble Space Telescope. Coming about due to a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the capabilities of its herald. It utilizes cutting-edge technology and a design optimized for studying the universe in remarkable detail. Unlike the Hubble, the JWST delivers clear and sharp pictures of distant heavenly bodies, working primarily in the infrared range. This unique feature allows it to penetrate cosmic dust and capture celestial objects that were previously hidden from our view. With its enormous 6.5-meter primary mirror, made out of 18 hexagonal segments, the JWST dwarfs the Hubble's mirror in size. Situated roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in a state of equilibrium with Earth, ensuring a stable and continuous view of the universe. While looking into the distant corners of the universe, exploring light years away also involves a form of time travel. The JWST uses infrared instruments to observe celestial objects and events going back billions of years. The light emitted by these objects, due to the expanding universe, undergoes a redshift, moving from the visible spectrum to the infrared range or longer wavelengths. Fortunately, the JWST can detect infrared light emitted by celestial bodies at extreme distances, enabling scientists to study the birth of stars, explore galaxy formation, and examine exoplanet atmospheres. Its latest notable discovery includes identifying an enormous mass of galaxies at the edge of the observable universe. This finding challenges the validity of the Big Bang theory, prompting a reassessment of our central cosmological assumptions. To better understand how we arrived at this point, let's take a brief journey through the history of space exploration. Early civilizations like the Greeks and Chinese laid the foundation for understanding planetary motion by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the early 20th century, Edwin Hubble, an influential space expert, made historic discoveries in cosmology and observational astronomy. His observations revealed that distant nebulae were separate galaxies, far beyond the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, formulated by him, showed that galaxies farther away were moving away at higher speeds, providing evidence for the expansion of the universe. The post-World War II period marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital flight in 1961, and the Apollo 11 moon landing in 1969 as landmark achievements. Fast forward to 1990 when the Hubble Space Telescope was launched, providing exceptional clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope highlights the steady development of our understanding of the universe. It revealed the vastness of space and changed fundamental ideas in astronomy. Take the Hubble Space Telescope, HST, for example. It captured the famous Pillars of Creation image in the Eagle Nebula, revealing a stellar nursery formed by massive columns of gas and dust. Another key achievement was the Hubble Deep Field, capturing thousands of galaxies in what appeared to be an empty patch of space. The HST also delved into exoplanet atmospheres, pinpointing elements like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Following the discovery of the closest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These accomplishments cemented the Hubble Space Telescope's legacy as a foundation of modern space science, captivating the world with its astounding astronomical discoveries. Its successor, the James Webb Space Telescope, JWST, was launched to build on technological advances and lessons learned from Hubble. One example is our understanding of the universe's origins, which today is explained by the prevailing theory of the Big Bang. Around 13.8 billion years ago, the universe began as a hot and dense singularity, rapidly expanding and giving rise to matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the various structures observed today. The Big Bang theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted, the Big Bang theory faced skepticism and challenges in its early years. Alternative models, such as the steady-state theory, proposed a universe without a specific beginning, and concerns arose about evidence supporting the initial singularity, the expansion mechanism, and observed anomalies. Many of these issues were addressed over time, with a critical piece of evidence coming with the detection of cosmic microwave background radiation in 1965, aligned with Big Bang predictions. Space missions like COBE and WMAP, alongside technological advances, further supported the theory. Precise measurements of cosmic microwave background radiation matched theoretical predictions remarkably well. Enter the James Webb Space Telescope, equipped with advanced infrared instruments capable of peering through cosmic dust clouds. Operating primarily in the infrared range, the JWST captures the oldest light in the universe, observing objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on star-forming regions, stellar nurseries, and the birth of stars, which are obscured from optical telescopes. Infrared light, with longer wavelengths than visible light, penetrates interstellar dust clouds, overcoming a limitation of the Hubble Space Telescope. The JWST can detect cooler objects emitting primarily in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light stretches, causing a redshift. JWST infrared capabilities detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Exciting events like black hole formations or new star births predominantly emit in the infrared range, further expanding JWST observational capabilities. The telescope can explore phenomena that would otherwise be hidden or invisible. JWST complements optical telescopes like Hubble by offering enhanced sensitivity and the ability to detect infrared radiation. This capability allows it to peer deeper into space and delve further into cosmic history, revealing hidden cosmic wonders and offering a broader perspective on the universe's development. The JWST serves as our window into the earlier stages of cosmic evolution. Recently, it uncovered something so astounding that it might prompt a reevaluation of the entire cosmological model of the universe. We've discovered vast masses of galaxies at the very edge of the observable universe. These ancient galaxies existed only a few 100 million years after the Big Bang, settling at the cosmic dawn. The astonishing part is that we're unsure how such massive structures formed so early in the universe's history. This discovery may lead us to reconsider our understanding of the formation and evolution of galaxies in the early universe. Studying early galaxies is crucial for unraveling the mysteries of cosmic beginnings. The JWST can provide insights into how galaxies, stars, and planetary systems emerged and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its expansion. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its primary constraint was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe, where these wavelengths are absorbed or distorted by cosmic dust and gas. The James Webb Space Telescope represents a remarkable leap in observing galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang, using its infrared sensitivity and advanced imaging capabilities. The JWST has revealed an abundance of ancient galaxies, offering unprecedented clarity and detail in understanding the universe's evolutionary history. Initial findings from JWST observations have stirred waves in established cosmological models. With detailed data challenging several aspects of prevailing theories, cosmologists are reassessing core principles governing our understanding of cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates among mainstream scientists. JWST observations have revealed a larger number of galaxies in the early universe than predicted by existing models, suggesting a more complex and rapid development process. Some observed early galaxies appear more mature than expected, challenging conventional models that predicted slower evolution. The discovery of an immense mass of galaxies challenges the assumed distribution and arrangement of large-scale structures, unveiling a more intricate and denser cosmic web than previously thought. These observations raise intriguing questions and avenues for further investigation. The existence of massive structures challenges early models of large-scale structure formation, prompting researchers to refine models for a better explanation. Understanding how such enormous structures gathered rapidly after the Big Bang presents a puzzle that requires an explanation that doesn't violate key principles of cosmology. Significant discrepancies in the conditions of the early universe compared to predictions based on existing models have also been revealed. These differences may suggest previously unknown physical processes, unexpected conditions, or unidentified astronomical phenomena. Simply put, these very variations have prompted scientists to reconsider and improve our models of the universe. Currently, all we can say is that further investigation is required to incorporate these surprising observations into a more comprehensive understanding of the universe's origin. Observations often provide exciting glimpses into the universe, but in-depth analysis sometimes uncovers discrepancies. For example, early observations might indicate specific properties or features within distant galaxies that, upon closer inspection, reveal differences in their formation, structure, or evolutionary pathways. In simple terms, cosmic phenomena are incredibly complex and require careful investigation for us to truly understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is one example. It involves analyzing the light emitted or absorbed by celestial entities. By examining the properties of the light, spectroscopy provides detailed information about the chemical composition, temperature, density, and motion of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial objects to the cosmic tapestry. The JWST has uncovered various instances where initial observations differed from later analysis. For instance, early observations of distant galaxies suggested a basic composition predominantly dominated by light elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic analysis using the JWST revealed intriguing variations in elemental signatures, identifying heavier elements or compounds previously undetected or underestimated in the early universe. This challenges conventional ideas about the early universe's chemical makeup and the processes responsible for their formation and distribution across cosmic distances. Moreover, initial assumptions about galaxies in the early universe were based on basic observations, suggesting a relatively uniform pattern of evolution and organization. However, broader investigations by the JWST uncovered a much more diverse and complex range of structural configurations within these galaxies. These differences have reshaped our understanding of evolutionary pathways, suggesting that the forces governing the structure and development of galaxies in the early universe may be far more complex than previously thought. On the other hand, the JWST has also confirmed some earlier theories and observations. For example, spectroscopic measurements by the JWST confirmed the presence of hydrogen, helium, carbon, oxygen, and nitrogen within celestial objects, supporting theoretical predictions. These findings align with the widely accepted lambda-cold dark matter model, which suggests the universe began with a Big Bang and consists of ordinary matter, dark and dark energy. However, Since some predictions of this model have been tested by later JWST discoveries, alternative possibilities, such as the cold dark matter model, which proposes that most of the universe's matter is dark matter, are being considered. This elusive matter, unlike recognizable atoms, doesn't interact with electromagnetic forces but exerts a gravitational effect. The model aligns with our understanding of cosmic microwave background radiation on a large cosmic scale, though challenges arise at smaller scales, where discrepancies exist in the model's predictions regarding the internal structure of galaxies and the abundance of small satellite galaxies around larger ones. Another proposition is the semi-steady-state cosmology, which suggests the universe follows a repeating pattern of continuous expansion and contraction, challenging the Big Bang singularity. This model remains speculative due to its deviation from traditional models and the lack of direct observational evidence supporting its cyclical nature. The mirror universe hypothesis proposes the existence of an identical parallel universe running alongside our observable universe. This model suggests the mirror universe may have its own distinct physical laws and particles, offering an alternative explanation for various cosmic mysteries. However, it lacks observational evidence or test data and remains largely speculative. The digital simulation hypothesis suggests our universe could be a complex programmatic simulation. Advocates argue that our existence may be a highly advanced simulation akin to virtual reality. This idea originates from philosophical considerations and faces challenges in providing observational confirmation or disproof. Finally, the multiverse hypothesis proposes the existence of multiple universes, each with its own distinct set of physical laws and properties. Our universe is just one among an infinite number of universes, each with different constants and possibly dimensions. While intriguing, we cannot directly observe or access other universes, making it speculative. While alternative cosmological theories may not be as widely accepted as the lambda cold dark matter model, it's important to remember that even the latter faced skepticism early on. Confirming or disproving these speculative theories is challenging, but they may warrant consideration if our current cosmological model falters over time. Recent discoveries, though eye-opening, have not disproven the Big Bang theory. According to many experts, observations from the James Webb Space Telescope have enhanced our understanding of cosmic history, aligning with Big Bang predictions. Huge galaxy groups at the farthest reaches of the observable universe suggest gravitational forces were at work even in the early universe, in line with the Big Bang's predictions. The presence of these massive structures at the edge of the observable universe implies their light has taken billions of years to reach us, offering a glimpse into the universe's past and supporting the theory's predictions about its evolution. However, these observations also present inconsistencies that merit objective scientific scrutiny. The JWST has opened new vistas, allowing us to explore the ancient realms of the universe. With the JWST, we face a cosmological landscape full of new questions and fascinating possibilities. These uncertainties challenge established cosmological principles, prompting a reevaluation of our understanding of the universe's birth, evolution, and fundamental laws. In light of such discoveries, it's crucial to remain open to rethinking our cosmic narratives. These new revelations are, however, just the preface to the ongoing journey of cosmic exploration, urging us to continue our quest for astronomical insights through further research and continuous advancement in the field of cosmology.